Hello everyone. In this video, we're going to see how fat is broken down to acetyl-CoA to get energy. So the person who figured out that fat is actually broken down in 2 carbon units at the time was Franz Crick in 1904, and he did a very clever experiment, simple experiment, but also very clever. So he fed animals. So he took a fatty acid, whether it was odd numbered or even numbered. He tried both. And in both cases, he put a tag at the very end, like a benzene ring. That's it. And then he asked, what kind of, how did the benzene ring look like when he fed these fatty acids, these modified fatty acids into animals? What did they do with it? So he fed it into dogs, actually. And he found that, when he fed the odd number carbon chain fatty acid, so the odd fatty acid, he always got benzoic acid. So he got the benzene plus 1 carbon. Okay. When he fed them even numbered fatty acids, he got phenylacetic acid. So phenylacetate, which has the 2 carbons on the benzene ring. Therefore, he deduced, okay, that the only way that this can happen is that if the carbon chain is broken down 2 carbons at a time. So it's very clear. So these are the 2 products, and depending on what you feed them, and so it really must move on processively from one end and all the way down to 2 carbons at a time. So now we know that the fatty acid breakdown yields acetyl-CoA, which of course is a direct input for the TCA cycle. We know very well what happens to acetyl-CoA once it enters the TCA cycle. So here now we have, let's say, one typical fatty acid, palmitate, 16 carbons total, and that will give you 8 acetyl-CoAs. So 16 divided by 2 equals 8 2-carbon units. Okay. So how do we break it down, however? Again, let's remind ourselves what the alpha carbon is and what the beta carbon is. So this is a carboxyl group on the fatty acid. Okay. So we have 16 carbons, let's say, on this particular one. And there is a carboxylic acid, the acid part of the fatty acid, and the carbon next to it is the alpha carbon, and the one next to it is the beta carbon. So when we start breaking down in 2 carbon units, what we're going to do is break this bond between the alpha and the beta carbons. Okay, that will release the 2 carbon unit. There it is. So it's gone, and now the last carbon has also to be oxidized to become a carboxyl group. So from the hydrocarbon situation that is shown here, it will become a carboxyl carbon in terms of the oxidation state. So really we have to solve 2 chemical problems. One is oxidize this carbon, the beta carbon, to a beta keto group. And we also have to stabilize the carbanion that will be produced once we break this bond right here between the alpha and beta carbons. So the second problem is actually quite easy to solve. So if you see the carbanion that's forming with acetyl-CoA, it can go back and forth. The electrons can go back and forth. The keto-enol tautomerization again, and that stabilizes the carbanion. So that's fine. Before we see how it's broken down, we have to discuss another situation here, how everything gets activated and how the fatty acid is broken down. Fatty acids are in the cytoplasm, but they're broken down actually in mitochondria. So they have to first be activated and then moved into mitochondria before they can be broken down. So we have a coenzyme A, and that's your fatty acid here. R is any chain, it doesn't matter. So we have coenzyme A and ATP. So we're going to use some energy here to actually activate the fatty acid. We're going to make a CoA, acyl-CoA group here, and we're going to break down ATP. The way that happens without acyl-CoA synthetase, so this is acyl-CoA, and the fatty acid will attack the alpha phosphate on ATP, okay? So it will be adenylated, so even the fatty acid gets adenylated in this case. Okay? That releases, of course, the 2 terminal phosphates of ATP to give you pyrophosphate. So we have the phosphate high energy bond hydrolysis there. It drives the reaction, and that's how you activate the whole compound. Once you have the fatty acid adenylate, then coenzyme A will attack. You release AMP, okay, and you have the acyl-CoA fatty acid. You have the thioester, okay, with CoA. Now that in that form, the fatty acid is ready to be broken down, except that it has to get into mitochondria first. So we have another spatial problem here. They're in different places where the substrate is and where the rest of the reactions happen. So the way it is brought into mitochondria is through a shuttle. Okay, it actually has to go deep inside the mitochondria, okay, in the matrix. So in the cytosol, there is a so the shuttle here is called the carnitine shuttle, and I'll show you in a minute what carnitine looks like. But the acyl-CoA that we saw, it was from the previous step. Now it makes an acyl-carnitine compound, which then gets transported by the translocase, and inside, once it's in the mitochondria, the acyl-carnitine becomes acyl-CoA again and frees up carnitine, and carnitine come out. So for every acyl-carnitine that you bring in, you bring another carnitine out, and the whole cycle can keep going. The palmitoyl transferase 1 and 2, the ones that do this reaction with carnitine, CPT1 and CPT2, the cytoplasmic and mitochondrial versions shown here in red and blue respectively, it turns out they're actually very important molecules, very important proteins. And this is how carnitine looks like. It's very small. And they're very important because they determine the rate at which fatty acids get broken down. All the other enzymes that we're going to see that are involved in the acyl-CoA breakdown in the mitochondria, they're not actually rate limiting for how fast you're going to break down the fatty acids. It's how fast you bring them in to mitochondria to be broken down. And that is mediated by these transferases that do the swap between acyl-CoA and carnitine. All right, so we got it in. We got the carnitine shuttle there, and we got it into the mitochondria, the acyl-CoA. Now, what happens at that point is we're going to break down we have to deal with the oxidation of the beta carbon. So how does that happen? First, we have to oxidize, and then we're going to break the bond. So this is the alpha and the beta carbon, okay? And we go stepwise. First, you make a double bond. You bring in a dehydrogenase, you make a double bond, then you hydrate, okay, you just add water, and then you put a carboxy carbon at the beta carbon. You put a hydroxy group on the beta carbon. Scratch what I just said in the previous sentence. So you hydroxylate the beta carbon, and then you oxidize that hydroxy group to a keto group with a straightforward, NAD dehydrogenase. Then you can finally break this alpha and beta carbon with thiolase, okay, which will release the last two carbons already in the acetyl-CoA, and it's going to make a new acyl-CoA that's chain that's 2 carbons shorter than what you started with. So that's the beta carbon again. So let's see. We have acyl-CoA. The first thing we do is we dehydrate. Sorry, the first we do is we oxidize to a double bond between the alpha and beta carbons. So that's the double bond we generate here. The enzyme is FAD dependent, and so for this double bond generation we use FAD. And if you want to know how this works, so this is a substrate. First one proton is picked up by participating acid on the protein, and now the whole hydrogen and the 2 electrons here move onto FAD to give you FADH and the more oxidized fatty acid, which is now unsaturated. All right. Once we get this double bond down, then we can easily hydrate it. So we put a hydroxy group, okay, on the beta carbon. So N-oyl-CoA hydratase will do the job. And once the hydroxy carbon is there, then we've seen many, many times how the hydrogenase and independent dehydrogenase can come in and generates a keto carbon. So now we oxidize the beta carbon. And finally, now we can break this bond, the alpha and beta carbon, and at this position. And the enzyme that does this is thiolase. What you get, so it uses another CoA comes in. Okay, so what you're going to get is the acetyl CoA from the very end, the last two carbons, this carbon. So we're going to break here. So these two carbons will release, will be released as acetyl CoA, and another coenzyme A will come in and make the new acyl CoA, which will be 2 carbons shorter. How that works, the enzyme we're going to see it again. So the way to see this is from bottom to top. That's a degradative form of the direction of thiolase in this case. We're going to see the red arrows later in another video, how we actually put together CoA units, acetyl CoA units. So in this case, the degradative one, you have to remember that there is first a sulfhydryl, so there is a sulfhydryl attack from the enzyme itself, and then that gets swapped with coenzyme A. All right. So this is a substrate. These are the last two carbons that are going to go away. Okay. This one here and this one in the form of coenzyme of acetyl CoA. So what happens? The beta carbon gets attacked by a sulfhydryl on the enzyme. Okay. So that breaks the bond. Okay. So you remove acetyl CoA, goes away, and what you have is an intermediate where the acyl part is attached to a sulfhydryl group, a cysteine on the enzyme. Then coenzyme A comes in, okay, here right at this point, and essentially you swap one sulfhydryl with another with a coenzyme A. So now you end up having a new acyl CoA, and you regenerate your enzyme. So this is how it works in the 4 steps that we saw, and you remove just 2 carbons to get acetyl CoA, and you have a new acyl CoA now. Oh, by the way, just so that you don't get confused, this is shown, this diagram here is shown as when you just combine 2 acetyl CoAs. But in this diagram here, it's as if we have a whole chain of acyl CoA, a whole chain of carbons. So the overview of the reactions are shown here with the key products. So when we oxidize the beta carbon, we picked up the electrons from the molecule, from the fatty acid. Where did the electrons go? Some went to FAD, and another pair went to NAD. So we generated FADH and NADH, and we know what happens to those molecules when they enter the electron transport chain. FADH will join through complex 2, and NADH through complex 1, and eventually all the electrons will get passed on, and you're going to build your proton gradient, you're going to get ATP. And also what we generate is acetyl CoA from just one round, okay, of beta carbon oxidation. So obviously acetyl CoA will go through the TCA cycle, generate more NADHs and one FADH, and so on and so forth. So it's going to generate more ATP from that. How much? Well, from one cycle then of fatty acid breakdown, from the one FADH we get about 1.5 ATPs, from one NADH about 2.5 ATPs, and one acetyl CoA going through the TCA cycle, you get about 10 ATPs. So a grand total from one round of fatty acid oxidation is 14 ATPs, ideally speaking. Okay. So if you have, for an even number fatty acid with so many carbons, whatever number of carbons, you have to say how many oxidation cycles do I need? So depending on how long it is, okay, minus 1 cycle, because the last 2 they just come out as acetyl CoA. For that one acetyl CoA, you add 10 ATPs. So you have n minus 1 oxidation cycles. So n minus 1 times 14, okay, plus the 10 that you're going to get from the last cycle, but you don't need really a cycle because it's going to come off as an acetyl CoA. But then from that, you have to subtract the 2 ATPs you used at the very beginning to activate the acyl CoA synthetase, to activate the fatty acid. So if you have a 16 carbon fatty acid, the N is the number of, that you divide by 2, that's going to be 8. So you're going to have 8 minus 1 cycles, because again, the last one is going to come off by itself as acetyl-CoA, times 14 that we calculated here. Okay, that's the number of ATPs. So 7 in this case times 14, plus the 10 you're going to get from the stump of acetyl-CoA that's going to be left, minus the 2 you spend in the beginning. That gives you 106 ATPs net profit if you burn 16 carbon fatty acid. So if you only have a 6 carbon, not a 16, but a 6 carbon fatty acid, that's a fairer comparison to glucose, by the way, which has 6 carbons. So how many ATPs are you going to get? You're going to get 36 ATPs, as it turns out. So this is only a modest gain compared to glucose. So if you break down carbon per carbon, if you break down, a 6 carbon fatty acid versus a 6 carbon sugar here, you get a little bit of a benefit, but not too much. However, the yield keeps increasing with length, so it's disproportionately so. When you go to 18 carbons, and all of a sudden you have a much more significant, so that's only 3 times longer than the 6 carbon fatty acid. And if you burn 3 glucoses, okay, you're going to get about 90 or so ATPs. But if you burn 18 long fatty acid, you get 120. That's a 20% profit. So it's even more substantial, and so on and so forth for even longer ones. And of course, the reason for that is obvious. Okay, the longer it is, the more electron-rich it is, the molecule, because you just have one carboxyl carbon all the time, but you increase the number of fully reduced carbons as you increase the length. So that explains the whole disproportionate increase in yield of ATPs. So length matters, right? So it's not beneficial to have short fatty acids. So that explains also why, again, they are such good energy reserves. You get a ton of ATP out of them because they're reduced. And again, they are less hydrated, so they occupy less space. So fatty acids are really incomparable as energy reserves compared to anything else. Now, this is a side story here. We saw how in ADP synthase, when you make ATP, you also get water, some water. That's part of the ATP reaction. There is the water. So if you use a lot of fat to feed your ATP synthase, your electron transport chain, acetyl-CoA electron transport chain, and then you make ATP, you're actually going to get quite a bit of water out in the end, which explains why desert animals have evolved this way, to store a lot of fat so that they can actually internally generate the water they need. Lastly, one little thing we had talked about when we talked about gluconeogenesis and biosynthesis in general, how burning fat doesn't help you in terms of making glucose or any biosynthetic, as a biosynthetic block anyway, because you cannot go to higher carbon numbers because of the TCA cycle, unless you have the glyoxylate cycle, which we don't. And that has been the dogma, and it's probably correct in most cases, but now more and more exceptions keep coming up. Somehow, if you label fatty acid carbon, when you break down the fatty acid, you shouldn't find this carbon labeled into bigger molecules, such as, let's say, nucleic acids, nucleotides, the NDP synthesis. But that's what these people found, not long ago in 2015. They found that the endothelial cells can actually bring in fatty acids. And again, the rate limiting part here was the carnitine palmitoyl transferase, the shuttle that brings in the fatty acid to mitochondria, to burns it to acetyl-CoA. It turns out that this carbon that was derived from fatty acid breakdown made it into DNA for some weird reason. We don't actually understand how this happened, but clearly acetyl-CoA can be used to make bigger molecules, at least in this case. So this concludes the story about breakdown. This is the standard for that standard, even numbered fatty acid that's fully reduced, no double bonds or anything like this. So we'll see in the next video some variations of the breakdown.